In the last class, we explored the transformer architecture, which achieved state-of-the-art performance on a variety of linguistic tasks. However, we will now examine its generalization ability more closely and discuss several limitations of the standard transformer model. Specifically, we will address three key limitations: poor length generalization, difficulty handling long sequences, and third, slow inference. The learning objectives of this lecture are to review the limitations of transformer-based models, explain state space models as a potential solution to these limitations, discuss how state space models can achieve both fast training and fast inference while maintaining good performance on long-range dependencies within a single architecture. Finally, review variants of state space models with a particular focus on the S4 and Mamba models. We begin this video lecture by briefly recalling the Chomsky hierarchy. It's a classification system of formal grammars and languages which categorizes different types of grammars based on their generative power. This hierarchy consists of 4 types of grammars, each associated with specific language classes. Type 3, regular languages, or regular grammars. These languages can be generated by regular grammars with simple production rules, typically involving a single non-terminal symbol on the left-hand side and a terminal or a terminal followed by a non-terminal on the right-hand side. These languages handle straightforward sequential patterns. Their rules dictate simply moving from one character to the next one or repeating a basic block. They are limited to recognizing patterns that do not involve complex nesting or keeping track of an arbitrary number of open or closed pairs. Context-free languages. These languages are generated by context-free grammars where the production rules allow a single non-terminal symbol on the left-hand side and a string of terminals or non-terminals on the right-hand side. These languages describe structured patterns where elements can be nested inside others, like parentheses in a math problem or clauses within a sentence. Context-sensitive languages. These languages are generated by grammars where the rules allow symbols to be rewritten in a context-dependent manner, describing patterns where elements influence each other. The rules for generating a part of the pattern depend on the surrounding parts. Recursively enumerable languages. These languages are generated by unrestricted grammars which have no restrictions on the production rules. These are the most powerful languages capable of describing any pattern that can be generated or understood by a step-by-step process, like a computer program. If there is a set of instructions that can produce a string of characters, this type of language can define it. We now move to the topic of length generalization in transformer-based models. A recent study by Deletang et al. Examined how well transformers generalize to new sequences that are longer than those seen during training. They investigated length generalization across different tasks, which were selected based on the Chomsky hierarchy. As stated before, in formal language theory, the Chomsky hierarchy classifies grammars according to the complexity of the languages they can generate. This hierarchy is equivalent to a classification of computational models known as automata, which is shown here on the right. Different types of automata can solve problems of varying complexity along this hierarchy. At the simplest end, automata with limited memory can only solve regular languages, which are at the bottom of the Chomsky hierarchy. At the other end, Turing machines with infinite memory and unrestricted access can solve all computable problems. Just as automata are mapped to levels of the Chomsky hierarchy, Deletang et al. Aimed to map various neural architectures to different levels of this hierarchy. To achieve this, they trained different neural architectures on tasks classified according to the Chomsky hierarchy, and then compared the model's performance on these tasks. The performance of these models on 3 tasks of increasing complexity from left to right is shown here. The models tested included transformers, RNNs, stack RNNs, tape RNNs, and LSTMs, as indicated in the legend. The vertical dashed red lines in each panel represents the maximum sequence length seen during training. For the parity check problem, the simplest of the 3 tasks, all models performed perfectly, generalizing well to longer sequences, except for transformers represented by the purple curve. The modular arithmetic task was more challenging, with all models showing a decrease in performance for longer sequences. However, transformers had the lowest accuracy among them. For the string duplication task, transformers performed significantly worse compared to other models like LSTMs or stack RNNs. Taken together, these results suggest that transformers struggle more with length generalization than other, even older architectures. This places them lower in the Chomsky hierarchy. We will now discuss another limitation of transformers: their difficulty in handling long sequences, typically those longer than 10 to the power of 4 tokens. This issue is different from length generalization, as we saw earlier, since the entire sequence is provided during training. The problem, as we will see, lies in the difficulty transformers face when dealing with very long sequences, even if they are given during training. One of the main challenges for sequence models, such as transformers, is handling sequences with long-range dependencies. Language processing, as well as other non-linguistic tasks, often requires reasoning over tens of thousands of time steps. To evaluate the ability of models to handle long-range dependencies, various tasks have been gathered in benchmarks such as the Long-Range Arena, or LRA. One of the most difficult tasks in this benchmark is the path X task, where the model is asked to determine whether there exists a path connecting 2 points. As shown in this table, which presents the leaderboard results for models from the end of 2020, all models, including standard transformers, failed the path X task. This demonstrates that transformers not only struggle to generalize to longer sequences they haven't seen before, but also face difficulties processing long sequences even when they are provided during training. The last limitation of transformers that we will review is their slow inference. During inference, to generate the next word in the sequence, a transformer needs to compute at each time step the self-attention matrix across all tokens. This means that the attention mechanism scales quadratically with the input sequence length, making it relatively slow. Since next token generation is done in an autoregressive manner, parallelization of the process is not possible. Other models, such as RNNs and CNNs, suffer from different limitations and offer various advantages. For example, RNNs on the left can integrate context from an unbounded number of path steps into their hidden state. However, as we saw in previous classes, RNNs suffer from the vanishing gradient problem, making them difficult to train. CNNs, in contrast, have a bounded context but can be easily optimized through parallelized computations during training. Lastly, continuous time models can handle continuous data with possibly irregular sampling. However, they are known to be inefficient and hard to train. So, how can we combine the strength of these models while overcoming their limitations? In this class, we will explore a new family of models called state space models, or SSMs, which aim to combine the advantages of previous models. Specifically, SSMs achieve both fast training like transformers and fast inference while maintaining strong performance on long-range dependencies in the data. SSMs implement a linear dynamical system that maps an input function, denoted as u, onto an output function, denoted as y. This mapping is performed through a latent variable x, along with a set of parameters noted here as capital A to D. Unlike transformers, SSMs rely on a recursive processing of the input, which, as we will see, provides an advantage during inference. As is often the case in deep learning, we will break down the model into multiple steps, where each step learns a local mapping between the previous step's output and the next step's input. This means that we will use the dynamical system described here as a building block in a larger model. This block will be repeated many times to form a deep model. The goal is to learn the final output of the model given its initial input by optimizing the parameters of all SSM blocks using standard gradient descent. We will show that by this we can achieve both fast training and inference, as well as good processing of long-range dependencies. The recurrent representation can provide us the advantage of RNNs, in particular linear time inference. For simplicity, we will assume that D equals 0, meaning there is no direct mapping within the SSM block between the input U and output Y. This can later be replaced with standard skip connections. We will also assume, for now, that the input signal U is one-dimensional, which is mapped onto a d-dimensional latent space X, and then back to a one-dimensional output Y. This means A, B, and C are all d-dimensional vectors. To understand the theory behind SSMs, we will now review the main conceptual parts of the model. The first step is discretization. The continuous dynamical system on the left, which maps continuous functions to functions, is discretized in time to produce a sequence-to-sequence mapping, similar to what we had with previous models such as transformers or RNNs. We apply discretization to switch from a continuous to a recurrent representation of the model. To discretize the time dimension, the first step is to determine the step size, which we denote here as delta, capital delta. Given a step size, the continuous input function can be discretized into bins, where the value of each bin is the value of the input U at time k multiplied by delta. The size of delta is a model parameter which will be estimated using gradient descent. Next, the dynamical system itself needs to be discretized. This can be done in various ways. Here we will use the trapezoidal rule from calculus. If we integrate both sides of the first equation of the dynamical system, the left side becomes x tn plus 1 minus x at tn. and the integral on the right-hand side can be approximated using the trapezoidal rule. Here, ft represents the entire right-hand side of the equation, so the integral is approximated as the sum of the right-hand side evaluated at times tn and tn plus 1, multiplied by half of delta. This gives the following expression for x n plus 1. After some additional algebra and a change of variables, the dynamical system can be rewritten in a simplified form, analogous to its continuous version. This is called the recurrent representation of the model, as it is expressed in terms of a recursive equation. The recurrent representation can be visualized as a recurrent network, similar to how RNNs are visualized, but without activation functions. Here, A is the recurrent matrix, B is the input matrix, C is the output matrix, and D, which we have assumed to be 0 for now, can be introduced as a skip connection if needed. After discretization, the next conceptual step is unrolling. By unrolling the recursive equations, we can transition from a recurrent to a convolutional representation of the model. This means that the model's output can be expressed as a convolution over its input. This is important because if the model can be represented in convolutional terms, we can leverage the advantages of CNNs, namely fast training through parallelization. Unrolling is achieved through simple algebra. Let's start with the recursive view. Assuming no states before time 0, the first state, x0, based on the recursive equation, is b u0. Given x0, we can compute all successive time steps. The next time step, x1, is a x0 plus b u1. But since we already have x0, we can substitute it, given x1 equals ab u0 plus b u1. Similarly, we can compute x2 by plugging in the previous time steps x1 and x0. This demonstrates that the state of the model at any time point can be expressed as a function of all inputs up to that point. We can apply the same process to the second equation of the model. First, y0 equals cx0, and all subsequent time steps can be computed based on the previous ones. This means that the output at time k can also be expressed as a function of all the inputs up to that time point and the model parameters. Importantly, this expression does not include the state variables xk. Looking closely at the resulting expression, we can see that the output yk can be expressed as a convolution between the input and a kernel, which depends on the model parameters. This kernel is referred to as the SSM convolutional kernel. To visualize this, here is an illustration of the kernel with length 4, as well as an illustration of the input vector with 0 padding before time 0. The first output at time 0 is the result of multiplying the kernel with the beginning of the pad input vector, which gives y0. The second output is obtained by multiplying the same kernel, now shifted by one time step, with the input values. Similarly, all remaining outputs of the model are computed by sliding the kernel across the input vector, multiplying it each time with the corresponding input values. In sum, we saw how a linear dynamical system which maps a continuous input to a continuous output function can be discretized to create a model for sequence-to-sequence mapping. This model can be represented either by recursive equations or in convolutional terms. This dual representation is important for achieving both fast training due to the convolutional representation and fast inference due to the recurrent representation. However, in practice, SSMs might perform poorly when long-range dependencies exist in the data. This is due to the common issue encountered in training RNNs, the vanishing and exploding gradient problem. The difficulty in capturing long-range dependencies arises from the propagation of gradients through many time steps, which depends on the recurrent matrix A. One solution to these gradient issues was to avoid learning the parameters of the recurrent matrix A. Instead, a fixed matrix is introduced that has a special property of preserving information from past states in the new state. The other parameters of the model still need to be learned. This special fixed matrix is called the Hippo matrix, which is based on the high-order polynomial projection operators theory, from which its name is derived. The Hippo matrix allows the state xt to memorize the history of the input ut, enabling the model to approximate relatively long sequences with a smaller number of units. The Hippo matrix achieves its memorization property by projecting the input signal onto a polynomial basis, such as the Legendre polynomials, ensuring an optimal approximation of past information. Here is an illustration of how the Hippo matrix works. The red lines represent an example of an input function that needs to be stored. The black bars are the values of the hidden states of the model. And the blue lines represent the corresponding Legendre series, which form the basis of orthogonal polynomials. That is, given any input, the Hippo matrix stores its information in the hidden states of the model by finding the required coefficients of the polynomial basis. We saw that the Hippo matrix approximates all the input signals seen so far into a vector of coefficients, which correspond to a polynomial basis. This is similar to Fourier decomposition, but with a key difference. The Hippo matrix stores the more recent signal more precisely compared to older signals. This is illustrated here with the input signal U in black and its approximation in red. The approximation is much more precise in the later time steps compared to the earlier ones. The blue curves represent the values of the state variables over time. However, calculating the kernel with Hippo can be computationally expensive. This may create a bottleneck in SSM computations, as the matrix A is repeatedly multiplied in the kernel. For example, given a hidden state dimensionality D and a sequence length L successive multiplications by A require O of D to the power of 2 times L operations and O D times L memory. To overcome this issue, Gu et al. Proposed a variant of SSMs called the S4 model, which limits the structure of the recurrent matrix to a spatial structure that is close to diagonal. This adjustment helps to speed up computations. Putting everything we've seen together, the SSM combines the benefits of both RNNs and CNNs, achieving fast training and fast inference while preserving strong performance on long-range dependencies using the hippo theory. We saw that the convolutional calculation can be parallelized because the output yk does not depend on the previous output yk-1. It only depends on the kernel and the input. During training, the entire input sequence of tokens is given, so parallelization is possible. During inference, the recursive view is used to infer one token at a time, with a constant amount of computation and memory required for each token. So far, we have assumed that the input and output signals are one-dimensional. In practice, both can be high-dimensional. In SSMs, each dimension is handled by an independent state space model. This is important for enabling parallelization during both training and inference. Additionally, SSM blocks can be stacked on top of each other to build deep models. Each SSM block can also be integrated into a standard neural network with features like dropout, etc. More recently, Gu and Dao proposed a new variant of SSMs called Mamba, which addresses several limitations of previous SSM models by introducing gating mechanisms similar to those in LSTMs to control the learning of the model's parameters. Gu and Dao showed that Mamba achieved state-of-the-art performance on various benchmarks, outperforming both transformer-based models and other SSMs. Here is the full title of the paper, so you can read more about Albert Gu's and Tri Dao's research work on selective state space. In this class, we saw that transformers struggle with length generalization tasks, face difficulties processing long sequences, such as in the path X task, and have slow inference. We also saw that to achieve both fast training and fast inference, we need to combine the advantages of RNNs and CNNs. SSMs offer a solution to this problem, successfully achieving this goal due to their dual nature. SSMs have various variants, in particular the Mamba model, which achieves state-of-the-art performance on a variety of tasks, outperforming transformer-based models. In sum, in the last lectures, we have seen several neural architectures that can be used for language modeling. We first saw the three levels of analysis of MAR to describe an information processing system. We then encountered the first neural architecture for language modeling, namely recurrent neural networks. RNNs process their inputs incrementally, generating an increasingly complex representation of the linguistic input in their hidden representations. However, they typically suffer from the vanishing and exploding gradients problem, and as a solution for this problem, we saw the long short-term memory units, LSTMs, which mitigate the problem significantly, allowing RNNs to capture long-range dependencies in the data. We next saw how convolutional neural networks, which were originally inspired by the function and structure of the mammalian visual cortex, can be adapted for the problem of language modeling. CNNs capture increasingly complex co-occurrence statistics in the data, which are useful for next word prediction. For translation tasks, we saw the encoder-decoder architectures with RNN units, and that they are limited due to an information bottleneck, and therefore achieving low performance on long sequences of words. To address this problem, attention mechanisms were introduced which allowed the decoder to selectively attend to different word embeddings in the input, creating a dynamic context vector on the fly. This led to the development of transformer-based models which rely solely on attention mechanisms, dropping recurrent connections altogether. This allowed parallelization and therefore to train transformers on large amount of data which led to new state-of-the-art performance achieved by these models. Finally, we saw that also transformers suffer from important limitations. In particular, length generalization, capturing complex long-range dependencies in the data, and slow inference. State space models overcome these limitations by combining the advantages of both RNNs and CNNs, using dual representations which allow both fast training and fast inference, while preserving good performance on long-range dependencies.